Hello, everyone. So here is the final video lecture, the final video on new information for semester one. And we are talking about infinite sums. So yesterday's topic was about finite sums. So if you just add a finite amount of terms, like 9 terms here, 12 terms there, you can do that. There's a couple of formulas. This is the formula if it is geometric. If it is arithmetic, then it's this one. It's this n over 2 times a1 plus an. But for either case, it's for a finite amount of terms. You just add the first one through the 17th one or the 20th one or whatever. What if you add an infinite amount of numbers? Um, what is the sum? First of all, let's realize that it's actually possible to add an infinite amount of numbers and get a real number, like a number somewhere on the number line. So here, this is pi, 3 plus 0.1 plus 0.04 plus 0.001, etc., all the way down the line. If you added up all these numbers, you would get the number pi. And since pi has an infinite amount of digits after the decimal point, you could break up those digits into an infinite amount of numbers. So that's one example where you can add an infinite amount of numbers and still get a number that's less than 4 even. But when we talk about adding or going out to infinity, a couple of words come into play in mathematics. Either it'll converge or diverge. And we've actually done something with this before with converging and diverging. Let me just remind you, if you have an arithmetic sequence, a sequence is just a list of numbers. So this first one, you keep on adding 0.5. And here we are adding 4 to get from one term to the next. Here you are adding 0.01. So the sequence, if I were to go out to the infinite term, like just keep on writing the sequence, hundreds and hundreds and hundreds of terms into the future, will I eventually start writing the same number over and over again? Or will I keep on writing a bigger number or a smaller number? And with all of these, it's just the number keeps on getting bigger. So all of these diverge. And with the series, an infinite arithmetic series, if you keep on adding the same amount for an infinite amount of times, you will eventually you will just be approaching infinity. So that diverges as well. So I hope that's clear. If it's arithmetic, in any case, it is always, always going to diverge. You're never going to have a sequence that converges. You're never going to have a series that converges. It just, you either are adding something, so you are approaching positive infinity, or you are subtracting something, so you're approaching negative infinity. You never land on a real number. That's not the case with geometric sequences. So here are 4 sequences. Do they converge or diverge? This first one, 2, -2, 2, -2, you are always multiplying by -1. Now, again, if you were to expand this out, hundreds and hundreds of terms into the future, will you eventually reach a spot where you're just writing the same number over again? If you are, then it converges to that number. But if you are not, then it diverges. Here, this one diverges. It always bounces back between -2 and +2, so it never gets closer to one of those. So this diverges. The second one, I'm always multiplying by 2, so the result is always getting bigger and bigger and bigger. So this one also diverges. This one approaches infinity. Here, what am I doing? How do I get from one term to the next? I always multiply by a half. So 1 times a half is a half times a half would be a fourth. If you keep on multiplying by a half, it will converge. These numbers will eventually be so close to 0 that it would be hard to even write the fraction, because it would be 1 divided by such a big number. It's essentially 0. So this sequence converges to 0. And this sequence, 88.8.08, etc., what is going on here? Well, you keep on dividing by 10. So as a multiplier, you keep on multiplying by 1/10. And the same thing here. This also converges to 0. Now those are sequences. When you have commas, that's a sequence. You're just listing the terms. A series is if you add all these up. Now, can you add an infinite amount of these things and have it actually land on a real number? So here, this is a geometric series. You take it from one term to the next, you multiply by 2. And I hope you can see this kind of easily, that you keep on the number that you're adding is getting bigger and bigger. It's always doubling. So this is just approaching infinity. When you add up these numbers, if you go out to infinity, your sum is going to approach infinity. So it diverges. But here, 5, 1.2, how am I getting from one term to the next? I am multiplying by 0.2. 5 times 0.2 is 1. 1 times 0.2 is 0.2. 0.2 times 0.2 is 0.04, etc. So the thing that I'm adding keeps on getting smaller and smaller and smaller. So eventually I'm going to add numbers that are essentially 0. So even if I add an infinite amount of those numbers, the sum will still be a finite number. So this one converges. And it actually converges to 6.25. But how do we figure that out? Because you can't add an infinite amount of numbers. So how do we figure this out? Well, before I go on, there's all sorts of sequences and series out there, but the two popular ones, not the only two, but the two, and for our test coming up, it's not just these two, but these two are popular: arithmetic and geometric. For arithmetic, when it goes out to infinity, there's no hope of it converging. It will always diverge. But for geometric, it's different. Some diverge, some converge. So how do I know the difference? Again, converging means for a series, for an infinite geometric series, if it converges, that means that if you add an infinite amount of numbers, you're going to get a real number. If it diverges, if you add an infinite amount of numbers, you're either going to get positive infinity or negative infinity. So this is the formula we know to find the sum of a finite, of n amount of a geometric sequence. But if I want to add an infinite amount, I would replace n with infinity. So that means I have to take r raised to an infinitely large power. And that seems kind of silly right now, so we'll just kind of investigate this. Let's take this. These are the two sequences in the last page. 5 plus 10 plus 20 plus 40. We know that the common ratio is 2, and this diverges. But let's just try to squeeze it into this formula. 5 times 1 minus r to the infinity. Well, 2 to the infinity is just an impossible number. It's just, we had to think of this as such a large number. It basically is infinity itself. And when you have infinity in the numerator, the whole, you take it, you have 1 minus infinity. This sounds weird, but that gives you a negative infinity. You're multiplying that by 5, and you're dividing it by -1. So the end result is just an infinity, because you're taking a negative divided by a negative. But this one is different because the r value here is 0.2, and 0.2 raised to an infinitely large power is essentially 0. Because if you keep on multiplying something by 0.2, you're just taking 20% of what was left over. So you keep on taking 20% and 20%, because 0.2 is the same thing as 20%. So if I gave you $100, and then the next day I said, okay, you can only keep 20% of that, that's $20. And then the next day I said, you can only keep 20% of that. And 20% of $20 is whatever that is. And then the next day, 20% of what is left over. It won't be long before you just have a penny, and then I'm going to take, you can only keep 20% of that. So you have just a small, it gets close to 0 very, very quickly. So when the r value was 0.2, this goes to 0, and 1 minus 0 is just 1. So the numerator is 5, divided by 1 minus 0.2, which is 0.8. And that's how I get this 6.25. 5 divided by 0.8 was 6.25. So I just used the same formula that we knew from yesterday. But this is the big conclusion for this little part. If the R value is bigger than 1, or if it's less than -1, then that series is going to diverge. You're either going to approach positive infinity or negative infinity. But if the R value is between -1 and 1, so this the absolute value is less than 1. So if the R value is between -1 and +1, somewhere in that range, of course, it's not going to be 0, then R to an infinite power will become 0, just like 0.2 raised to the infinite power is 0. And that means the entire series will converge, because 1 minus 0 is just 1, and you're just left with this 5, which is the A1 term. All right, last slide. 4 examples. Let's see. So I got 4 geometric series. And do they converge? Yes or no? And it's all about that R value. If the R value is bigger than 1 or less than -1, it diverges. But if it's between -1 and 1, then we get to use this formula to find out what it converges to. So it's all about finding that R. This sequence, this series, how do I get from one term to the next? What am I multiplying over and over and over again? You are, the numerator is staying the same. So you've got 1 in the numerator, but what do you have in the denominator? In the denominator, you're dividing by 2. 64 is being divided by 2. That gets you 32. 32 is being divided by 2, so that's 16. 16 divided by 2 gives you 8, etc. So to get from this fraction to this fraction, you would multiply by 1 over, come on, 1 over 1/2, right? 1 divided by 1/2. You keep on multiplying 1 divided by 1/2. And 1 divided by 1/2 is the same thing as 2. We're just doubling. To get from this term to the next term, I just multiply by 2. So the R value is 2, and since the R that's bigger than 1, this will diverge. This will go to infinity, and you can already see it getting too big over here. You're adding 3. The next term I would add would be 6, and then 12, and then 24, and then 48. So it would get big very, very quickly. Here, what is the R value? How do I get from one term to the next? Here I multiply by -5 to get from -1 to 5, and then multiply by -5 again to get to -25. So the R value is, this case, is less than -1, so it again diverges. This one, how do I get from one term to the next, etc., etc.? I hope you can see here you're dividing the whole term by 2. So in other words, you're multiplying by 1/2. And aha, 1/2 is between -1 and 1. So it converges. Again, because if you take -1 to an infinite power, you're basically going to get 0. So that means I get to use that formula. So 1 over R to the infinity, so 1/2 to the infinity would just become 0. So what does this simplify to? The numerator would just be 100, because this parentheses, you have 1 minus 0, so it's just 100 times 1, so it's 100. The denominator is 1/2, and 100 divided by 1/2 is 200. Now this should be kind of mind-blowing to us, and we're almost done. This is the last one. But just realize what's going on. Here, I've got literally an infinite amount of numbers that I'm adding. Of course, I can't write them, so I write ... But there, it keeps on going. So if you were to add an infinite amount of these numbers, it would add up to exactly 200. This one, from one term to the next, to the next, to the next, what is the common ratio? I hope you can see that it is negative 1/3. So this converges again because r is between negative 1 and 1. So I get to use my formula, negative 1/3 to the infinite power. This would essentially become 0, so I don't have to worry about it. So in the numerator, in the parentheses, I basically have 1 minus 0, which is just 1. So the whole numerator would just simplify to 2. But don't forget these negatives are slippery, and I made a mistake when I was preparing for this. I forgot the negative down here. It's 1 minus r. R is negative 1/3. So 1 minus negative 1/3 gives you 4/3. And 2 divided by 4/3 is the same thing as 2 times 3/4, which is 3/2. So 1.5. The whole thing adds up to 1.5. You start with 2, you add negative 2/3, you add 2/9, you add negative 2/27, and so on for an infinite amount of terms. You will add up to 1.5.